So we're going to talk a lot about acids and bases. We're going to work with amines, which are nitrogen-containing compounds. So nitrogen is element number 7 on the periodic table. It likes to have 3 bonds to it and a lone pair of electrons. When we think about our periodic trends, it's also pretty electronegative, but not as electronegative as fluorine or oxygen. So because it's not as electronegative, it's a better nucleophile. Also, if you'll recall Markovnikov's rule, which talks about where some substitution alkene happens, and Zaitsev's rule, which tells us a little bit about where we want to have the most amount of substitution with alkenes. So these will come back up today. So if these are unfamiliar terms to you, just take a quick look and review these terms when you're studying this chapter. All right, we only have 2 learning objectives today, but they're going to get into a lot of mechanisms and a lot of nuances. So yeah, we'll just jump right into that. All right. So I'm going to do just a really quick review here for you all of some naming things that we've talked about. So we're going to have some intermediates here, and I want to make sure everyone's on the same page. So we had talked previously about this compound here being called an imine. And specifically, we can say, if that came from a ketone, so those 2 R groups are not hydrogen, then we have a ketamine, which is the name of a functional group. This came from an aldehyde, and this is called an aldamine. Right, so oftentimes we don't specify that, but that's just helpful to know kind of where our naming conventions come from. So when we protonate an imine, we're going to get an iminium. So we're going to add an H and a plus to that, and this is an iminium ion. Right, so we've seen before when we add a proton to something and when it's cationic, we get this IUM at the end of the word. So that just means it's cationic. So we've seen ammonium salts. These are iminium salts. We've seen a lot of examples of this. So last chapter we learned about, last lecture we learned about some acetals and ketals. And the intermediate, as we're making these in our mechanism, was called a hemiacetal. Here we're dealing with amines, so we have a hemiaminal. All right, so this is kind of halfway to where we're getting to, so a hemiaminal. And then the final thing that we're going to talk about today extensively is going to be an enamine. All right, so enamine. You'll hear some people say this is enamine. It kind of looks like it should be pronounced that way. But as you'll recall, I said previously, I like people to remind people that there's an alkene in here. So I say enamine. So there's an alkene and amine. All right, so we're going to talk about these during mechanisms. So, I always like to have people on the same page here so that when I say terms, it's not super confusing. So, we'll notice some really special things here. So today we're going to learn how to make imines and enamines, but we're going to see these other 2 compounds as intermediates. All right, let's jump into our learning objectives. This is learning objective 18M. This is going to be the 4 P's for the formation of imines. And we can form these from ketones / aldehydes. And very specifically, primary amines. So we can also say 1 with a degree symbol for primary amines. And this is in chapter 18.10. All right, so if we use a secondary amine, the product that we get out is not an imine, all right? We are either going to get iminium and stop there or get an enamine. So this is a very special type of example, and we need to recall that this is just primary amines. Oftentimes we combine 2 things and they make the same functional group, not in this case. So, all right, so we're gonna have our primary amine. So primary meaning there's only one thing bound to it. It has 2 hydrogens and 1 R group. All right, R group is some carbon-based group. You can do this with a lot of different types of amines. And this is going to be our nucleophile in the reaction. We can probably already predict that because we know that it has a lone pair of electrons, and amines, nitrogen-containing compounds are often quite nucleophilic. So the other part of our learning objective is going to tell us the other compound that we're going to use is either an aldehyde or a ketone. And you'll recall from the last slide that we can make an aldamine or a ketamine, depending on what we started out with, the aldehyde or the ketone. And in this reaction, this is going to be our electrophile. All right, so very importantly, oftentimes we kind of just use whatever acid we want. In this case, and I'm going to tell you why, we can't necessarily do that. So we need to have a weakly acidic solution at about pH of 5. All right, so a good acid to use for this would be tosic acid. This is non-aqueous acid, so we can just add a small amount in and get to a pH 5 solution. And I'll tell you why that is when we take a look at the mechanism. All right, so we get out an imine, which is double bonded to a nitrogen. Kind of looks like a ketone, but with the amine. Sometimes people call these Schiff bases. I don't really use that term because I don't think it's very helpful. I use the term imine, but you might see this in your book as a Schiff base. And then it's always helpful, to draw the byproducts of this reaction. So at the end of the day, we now can see, because we formed water, we can see that this oxygen is coming from our aldehyde or our ketone. The other thing we can see is we have 2 hydrogens, and those 2 hydrogens came from our primary amine. Right, if we had a secondary amine with 2 R groups on it and 1 hydrogen, we could never get to this product. Because we would have too many hydrogens. All right, we're going to need to do some proton transfers. All right, so as I said before, we need to think about the fact that this has an acid catalyst that keeps the solution at pH 5. All right, and this is because amines are very basic. So if we have a very strong acid, we don't want to protonate that nucleophile because then it won't be a nucleophile anymore. All right. So don't want too strong of an acid to protonate the amine. The reason is if we lose that lone pair of electrons, those are electrons that's going to act as a nucleophile, right? So then would not be a nucleophile anymore. That would just sit there. Right, and I'll in the context of the mechanism, I'll explain that as well, all right? But if we protonate something, previously our nucleophiles weren't very nucleophilic when we were making acetals and ketals, right? We're going or hemiacetals, like or hydrates. We're using oxygen-based nucleophiles. Those are not very nucleophilic, but they're also not very basic. So we didn't worry about protonating those, but we do worry about protonating our amines. So there's a class of reactions that this is. This is called a condensation reaction. All right, so a condensation reaction means that you lose a small molecule. We've seen condensation reactions before. In this case, it's water. So it's kind of easy to remember, right? You have condensation on your car in the morning when it's cold, and that's water. So condensation can be lost with any small molecule, but we often see water as our small molecule. So, of course, I drew equilibrium arrows under our reaction, and so we can drive our reaction forward by removing water. Right? And this is the very first reaction that I ran in the research lab was an imine condensation. I used a Dean Stark trap and I used tosic acid and I condensed 8-aminoquinoline onto a dione. I still remember that's the very first reaction I ever ran as an undergraduate in the research lab, was this very reaction. So I'm always really excited to teach you all things that really inspired me. I made a molecule no one had ever made before, ever in the world, ever in the history of time. And I just thought that was the coolest thing. All right, let's take a look at P4 and help us understand why we need this weakly acidic solution. All right. Okay, so we're going to start out. Let's start out with an amine. Let's use methylamine. That's a pretty simple amine. All right. And we can use a ketone in this example, acetophenone. You'll recall that this is named. So instead of using tosic acid, I'm just going to use H3O plus as our source. So we have H3O plus in this reaction, and we have H2O, right? We could drive this reaction forward by removing that water, but ultimately we're going to have a small amount of it. So this is a case where we don't want to have too much H3O plus around because our amine is very basic. That has a pKa, or the protonated version has a pKa of maybe 10 or 11. So it's far more basic than water. And so we would get that protonated. Right, unlike when we've seen before with acid catalyzed reactions, our acid catalyst here is just going to be there for proton transfer. We're actually not going to go ahead and protonate this oxygen here. The reason is that our amine is more basic, so oxygen would not be protonated in the presence of the amine. But instead, because we have this weakly acidic solution, we can go ahead and just take the lone pair of electrons on our nitrogen and have it attract that electrophilic position at that 1,2 position at the base of our carbonyl. That means we're going to break our OH bond and we're going to place the lone pair of electrons on our oxygen, right? Whenever we're breaking a bond is just a set of electrons. And so we need to put those somewhere, and that's at the top of our oxygen. All right, so we've made the bond right away that we need to make. I'm going to draw a negatively charged intermediate here. We really do not like to see negatively charged intermediates in the presence of acid, right? But this is a very, very weakly acidic solution, all right? So I'm going to draw a series of arrows in 2 steps, all right? The reason is that a reaction, things usually happen one at a time, but you could switch the order of these steps if you wanted. So essentially at the end of the day, we're trying to get to a neutral species. So we need to take care of this negative charge by protonating it. We need to take care of this positive charge by deprotonating it. And the order in which you do that in does not really matter. Your book shows that it happens at the same time, but that's actually not likely. The other thing people often get confused about is they say, well, why can't this negative charge just come down and deprotonate that NH bond to neutralize it? Well, the reason that doesn't happen is that geometry is disfavored. That lone pair of electrons can't quite get around to pick up that proton. All right, so we're going to take our water. We're just going to deprotonate our ammonium salt, which is our protonated amine. That's going to form our neutral species on our nitrogen, and then we'll take care of the negative charge at our oxygen first. Oops, that should be a methyl. And as I said before, I don't care the order that you do this in. I don't think that anyone knows the order that this particular set of steps is. All we're just doing is proton transfers. So we ended up with H3O plus is the product of that reaction, that arrow that we just did. And so our negative charge and lone pair of electrons on oxygen can deprotonate that H3O plus. So the proton transfers don't really matter that order. All we're doing is trying to get to this neutral species. Right, so now our oxygen is neutral because we've protonated it. That's great. And our amine is neutral because we've deprotonated it as well. Right, so you'll recall that this is a name that we learned earlier today. This is a hemi aminal. All right, so when we have a nitrogen and an oxygen bound to that same carbon, each with a single bond, we have a hemi aminal. Okay, so this kind of follows the same pattern we've seen before, where a nucleophile attacks a carbonyl, then we do some proton transfers to get to a intermediate, right? We saw this in acetal formation and ketal formation as an intermediate. So we can kind of see that this is likely going to proceed through similar mechanisms that we've seen before. So in this case, what we need, right, what we're looking for is to form two bonds to our carbon here from our nitrogen, and we're also looking to lose a small molecule of water, right? So when we take a look at this intermediate, we say to ourselves, doesn't look good to lose OH, so why don't we go ahead and let's protonate that intermediate. So we had reformed our acid before, and this is why we have an acid catalyst. We just have some of it around. Actually, we had reformed water in this case, but we have an acid catalyst for our proton transfer. And let's go ahead and protonate our oxygen to make it into a better leaving group. All right, so that is going to go ahead and have our oxygen be positively charged because we put two protons on it. And this is looking like a pretty good candidate for a leaving group. All right, so at the end of the day, we need to make a double bond to our carbon there with our nitrogen. And we have our leaving group that is primed to leave. So we use that lone pair assisted mechanism we've seen before. The lone pair on the nitrogen comes down, forms a CN double bond, and then that causes the OH bond to break and go as a leaving group. All right, so now we've lost oxygen bound to two hydrogens, which makes it into water. We have now made a nice double bond between our nitrogen and our carbon with our amine. We still have a proton on that amine, so that means it's an iminium ion. This is one of those intermediates that we've seen before. Iminium ion. And we're very close to being able to get to our final product, which is the neutral species, right? We've made all the bonds that we need to make to get to our final product that we're looking for based on our learning objective. Now we just need to go ahead, regenerate our acid catalyst, and we can do that by taking water, whether it's the water we lost or water that we added in. So we protonate that NH bond. We break that NH bond and return bonds for our aminium or to our nitrogen. And what we get out at the end is going to be our imine. All right, so this is reminiscent of some of the mechanisms we've seen before. We've seen before things like this lone pair assisted leaving of water. We've seen a lot of proton transfers before. So it's the same part of the pattern, but the difference here is that we don't protonate either our electrophile or our nucleophile. We've basically made our nucleophile into a better nucleophile, so we don't need our electrophile to be a better electrophile. All right, so that's our mechanism of imine formation. All right, so I told you that we have a primary amine only, right? In this mechanism, we see we have to lose both of these NHs. They end up on our water, so that's why we need a primary amine. to form an imine. So what if we have a secondary amine? Well, we're going to sometimes be able to form a different functional group, which is our enamine. All right, this is going to be learning objective 18. I have it written as N, just want to double check that. Learning objective 18N. This is another mechanism question. So it's the 4 P's of formation of enamines from aldehydes and ketones. So starting with the same functional groups as our starting material, and secondary amines. If you wanted to follow along, this is in chapter 18.11. All right, so we need some special requirements for our aldehydes and ketones, all right? So it can't just be any aldehyde and ketone. Let's take a look at what we can and cannot use. So we can have our secondary amine here. So just one NH bond. This is going to serve as our nucleophile in the reaction. Makes sense. We have that nitrogen with that lone pair, very nucleophilic. All right. So now we need to have an aldehyde or a ketone that specifically has an alpha CH bond. So we have to have this alpha CH bond. Right, we learned about the naming of this, and we said this is the alpha position. All right, so we need an alpha CH. All right, and this is going to be our electrophile. All right, we're going to see in the mechanism why we need that. All right, this is also at pH 5. It is a condensation reaction, but there's other irreversible steps, so we draw it as an irreversible arrow, not as equilibrium. All right, so now let's see what our product is. We have R1, and then we're going to have a double bond in our product, right? This is our enamine that's going to form here. We're going to have a single bond to our nitrogen. So this is our enamine. Right, and our water is going to come as our byproduct. What we see is that one proton came from the amine. Right, our secondary amine, we only have one proton there. And then on this side, we see this came from our alpha CH bond. All right, so that's where our byproduct is coming from. It's much easier to see mechanisms if you know where your byproducts are coming from. All right, so it's not from a. And again, the optimal acidity is going to be pH 5, so slightly acidic. So this helps with our proton transfers. Allows them to sort of be facile. We have a little bit of acid that can shuttle those protons around, but not so much so that we are going to protonate our nucleophile. And so again, we like lactosic acid for this reaction as well. You could play around with other acids. It just needs to be mildly acidic, but lactosic acid is a nice one to remember. Okay. So I'm going to, all right, before we get into the mechanism, we need to be able to recognize these patterns. I think a lot of times people on exams are like, oh, an amine and a ketone gives us a condensation reaction that is important, but that's not what's going on in this case. So let's go ahead and take a look at a CHEM question. To sort of solidify our learning here and see if this is going to start to make sense. We'll do a couple of CHEM questions. So leave your phones out, but they're not going to be right in a row. All right, so this is going to be our first chime-in question, which we think about what product would form in this reaction. The pattern recognition is quite important here. Sometimes trying it on your own before we really get into it is kind of helpful. Right, would highly recommend that whenever we're looking at these questions, whether it's in chime-in or an exam, we take a look at the type of amine do we have. Do we have a primary amine? Do we have a secondary amine? Do we have a tertiary amine? What is our amine? The other thing I would encourage you to take a look at is, do we have alpha CH bonds in our substrate, right? Both of those things need to be there if we're going to form an enamine. And the requirements for forming an imine are going to be different as well. All right. So let's see what people are thinking here. All right. So this is a difficult thing to recognize, right? So let's go ahead and go over this answer. And the answer is in fact C, but we're pretty evenly split here. So let's go ahead and take a look at this chime-in question. All right, so our chime-in was asking us if we have our ketone here. I'll draw this in as CH3 instead of just that dash. Sometimes it's helpful to draw out chemical structures. And we have a secondary amine. And here we have 3 alpha CH bonds. All right. So that means in this reaction, the products of this reaction, I'll write out all the examples. All right. So one of the answers that we had was our imine. But here we've lost an ethyl group. All right, we started with a secondary amine and we end up with 1 here. That's wrong. Okay, so now let's take a look at our second answer that we had up there. We had a double bond in this, and we have not lost our ethyl groups. So that's great. But we'll notice here that we have 5 bonds to carbon. Right? So we can't have 5 bonds to carbon in that situation. So this is not right. So what we would do is we would take a look at the final suggestion, and we would say this final suggestion has a secondary amine represented in it. So that's correct. And then it has a methylene unit there. So 2 CHs. And when we took a look at our byproducts and our products of our reaction in this here, we see our enamine is going to have only 2 groups on it. It's going to be an alkene, and then we're going to lose an alpha CH bond. And so that is what we can kind of do a critical assessment of this chime-in question as we're thinking about that. All right, so don't worry, we'll do many more examples. And before we get into our next chime-in question, I just want to cover recalling Zaitsev's rule. This you learned in 2301. All right, and in this case, unsymmetrical ketones with multiple alpha CH bonds form the more substituted alkene. All right, so I should also say ketones or aldehydes. If you have an aldehyde, you don't pluck off the aldehyde CH bond. That's not in the alpha position, but you could have an alpha CH bond on the other side. Okay, so what do I mean by this? If we have this ketone here, right, and I'm going to suggestively draw in our CH bonds here. All right, so Zyseth's rule says that if we bring in our amine, let's use dimethylamine. So this is a secondary amine. That should be our key. Do we have our two requirements to form an enamine? We do. We have our secondary amine. We have a ketone or aldehyde with alpha CH bonds. All right. So we could get two products out of this reaction. All right. So we could either get this product here, where our nitrogen has a single bond to it, and we've taken off the alpha CH bond from the position that is on the left. Or we can also form the following, where we've taken the alpha CH bond from the group on the right. All right, so we love always to make more substituted alkenes, right? That's what you learned in 2301. Always make the more substituted alkene if you have the option to do it. So that means that this is the more substituted alkene here. And this is the more favored product. Even though we had more, the number of CH bonds that we had was greater, at the end of the day, the more substituted alkene is going to govern the reaction and the stability of that. All right. So not only do we have to think about if we have alpha CH bonds and if we have a secondary amine, we also need to start to think about where we're actually going to do that deprotonation of our alpha CH bond and the mechanism I'm going to show you shortly. Okay, so let's practice that with a chime-in question, all right? I'm going to close this other question, and let's go to our next question. So here we have our options, all right? So we can think about this in terms of our secondary amine. Do we have that? Do we have alpha CH bonds? Looks like we have multiple positions that have alpha CH bonds. So go ahead and think about what you think the product of this reaction is going to end up as based on Zyseth's rule. All right, so when we're taking a look at this, we see that A is an iminium ion, all right? So that's not the product that we get out with a secondary amine and a ketone or aldehyde with alpha CH bonds. I will tell you it's an intermediate in this reaction, but that's not the final product. At the end of the day, the final product is an enamine. So that means we're choosing between B and C. Let's see what you all think. All right, so the B's have it because the B answer has that more substituted alkene. All right, so let me go ahead and draw this out for you all. All right, so let's take our second chime-in question. Think about this. Okay, so the substrate that we were given, the compound we were given, was this ketone. Has a lot of branching on it, but remember, we know the naming of our ketones, and this is the alpha position on both sides. We have our alpha position. All right, so now we can think about, does our alpha position have CHs? Well, carbon always has 4 bonds to it, so we have 1 bond, 2 bonds, 3 bonds. That means we are looking for a CH bond that is drawn in there. Now we have 4 bonds to carbon. We take a look over here. We have the alpha position. We have 1 bond to that carbon, 2 bonds. That means we have 2 CHs that we can choose from. All right. And then we take a look at our amine and we say, okay, is this a secondary amine? And it in fact is. All right. So we have met our 2 requirements for enamine formation. We have a secondary amine and we have some alpha CH bonds. All right. So let's take an evaluation of all of the different answers that were given. So I think people got this one a little bit more easily than the other one. but just in case, let's go ahead and go through each of the answers. So this is not our answer because this is not an enamine, right? This is a minium ion. It's positively charged. It is going to be intermediate in our mechanism, but we know that if we meet our two requirements of a secondary amine with alpha CH, we're going to form an enamine, and that's not what this is. Okay, so we have a couple of options then for which of our enamines we're going to form. I'm actually going to draw this a little bit. Oops. Draw this a little bit lower. All right, so we have our 5-membered cyclic amine that's called pyrrolidine. Okay, so here's an option. We do have an enamine. So this could potentially be the correct product. We know that's the correct product of these two starting materials. But we also have the option in which we can form our enamine with a double bond at the other carbon. All right. Both of these have alpha positions. Here's alpha. All right. And we look at our starting materials. This is also an enamine, but Zeitzeth's rule tells us that we need the most substituted carbon for our alkene. So we have 1, 2, 3, 4 groups, a tetrasubstituted alkene versus 1, 2, 3 groups for a tri-substituted alkene. All right. So this is the correct answer with B. This is a tri-substituted. This one is the tetrasubstituted alkene. So that's why we know that it is correct. Right? Versus this is a tri-substituted alkene. And tetra is more than tri, all right? So we are governed by our product identity. All right, so this is why I wanted to spend a lot of time on this particular, just 2 learning objectives today. We still need to go over the mechanism, but we need to make sure we know in the mechanism which thing to deprotonate at the alpha position if we have 2 options, all right? That's why we need to understand this idea of these 2 compounds that we could have formed, and that the middle imine is the correct one. All right, let's get into the mechanism though. All right, so let's start out with a ketone. I'll suggestively draw in CH3, but with an alpha proton. All right, we don't need to worry about that yet, but we just want to check our starting material. Do we in fact have an alpha proton? And we do in fact have an alpha proton. In this case, we're not going to worry about which alpha proton to take because we only have one of them. Let me draw out this benzene ring for you so that you can check for yourself that we only have a single alpha proton. Well, when we have a benzene ring, we have H's here, but these are in the beta position. All right, we don't need those. We don't care. Great, they're in the beta position. That's not going to help us. All right, so we do have an alpha CH bond in this compound. All right, so that means our mechanism is going to proceed. We're going to have methylamine as our amine. So it's a secondary amine. It has 1 NH bond. All right. So we're going to start out at equilibrium because some of these are equilibrium steps, but at the end of the day, this is a irreversible reaction, and we'll see why. All right, so we're going to take our lone pair of electrons on our amine. We're going to go ahead and attack our carbonyl carbon. We're not going to worry about the fact that our alpha CH bonds are there. We're going to deal with them later. We just wanted to confirm that we could do this mechanism with this intermediate. So we're going to get a very similar intermediate that we saw before. I'm going to abbreviate this as phenol just so it's easier to draw. All right, we've returned that double bond as a lone pair of electrons on our oxygen. We're going to go ahead and see that our amine has 2 methyl groups on it. It still has its NH, so it's positively charged. This is exactly what we saw before, right? This is a intermediate that we've seen before. We've seen that we can go ahead and use our acid catalyst and our water in the reaction to go ahead. And again, the steps, order these steps doesn't matter. To do this proton transfer, we want to get to our hemiaminal, which is a neutral species. All right, this is the exact same as the mechanism that we saw before. We're going to see where it goes differently. But if you wanted to protonate your negatively charged oxygen before you deprotonated your positively charged ammonium, that would be fine too. All right, this is exactly what we saw before. All right. So we have made some acid in that step. That was our byproduct of this reaction. So now we can get ready for this next proton transfer to sort of quench that negative charge and give us a neutral species. All right, I'll do some equilibrium arrows. We'll bring this down. The compound that we make is going to be neutral. Our oxygen is now protonated. And our amine is neutral as well. Nothing's changed on the bottom. All right, this is our hemiaminal. We've seen this intermediate before. All right, so this is the exact same as the mechanism that we saw before. But what we were doing before is we were forming an imine, not an enamine. But we're actually going to go through that same intermediate, okay? So just like we saw before, we're going to create a good leaving group. All right. We have our H3O plus that's still here. All right, just like we saw before, we want water to leave in this reaction. So we're going to go ahead, we'll protonate that, deprotonate that OH to form water. Setting up our leaving group as water to be a good leaving group. Ultimately, at the end of the day, I'm drawing these both in as sort of blue hydrogens, but proton transfers, we have a lot of different hydrogens coming from a lot of places. Right, this is the same intermediate we saw before in imine formation. We're gonna again use that lone pair assisted, getting rid of our water through that lone pair assisted nitrogen. So the nitrogen on the lone pair is going to assist the leaving group, that's water. So we've lost water in this reaction. We're going to get to a similar looking intermediate that we saw before. This is the exact same that we saw before for our mechanism. All right, the mechanism is totally the same as we had before, but the difference is our iminium ion cannot be deprotonated. All right, so I'm going to scroll. I'll give everyone a moment to catch up, and then I'm going to scroll back to what we had seen before. You'll see that it's the exact same. We'll see where we differ. All right, so when we look back up at our mechanism that we drew for imine formation, we're here, this iminium ion. Now the difference is in our imine forming case where we form this is an NH bond, all right? We can have water deprotonate it, get us to our neutral species. We scroll down here and we see that we don't have an NH bond. This water cannot come in and deprotonate an NH bond on a positively charged nitrogen. So this is where we come in and we have our alpha CH bond that can come in and bring our reaction home. All right, so we have a couple of choices here. We have 3 alpha CH bonds. This is where a mechanism differs, all right? So this water is going to come in. It's not going to deprotonate an NH bond. It's going to deprotonate a CH bond. That CH bond is going to break. It's going to form a double bond between our two carbons. That forms our amine of our enamine. I should do this in a different color. That forms our alkene. And now this carbon bound to the nitrogen twice has too many bonds to it, so we need to break that NH bond and return those electrons to our amine. So there's actually 3 arrows here. 1, 2, 3. In this particular step, it's a cascade. And then that's going to get us to our final product, which is our enamine, right? We still have 2 alpha CH bonds. We just needed to deprotonate 1. And now we get to our neutral species, which is our enamine. All right. So this is where the mechanism differs here. All right. It's just at this key step that the mechanism is different. All right. So they're basically the same, but we have no positively charged NH. All right, I'm going to do in my final minute, I'm going to do just a really quick practice problem for you, where if we have a primary amine versus a secondary amine, doesn't matter if we have the same ketone for both, we're going to end up with different products. So if we have a primary amine, we're going to form an imine. And if we have a secondary amine, we're going to form that enamine, even if we have that same ketone. All right. So those are the products that we form. All right. So recall for this, we got to really be careful with knowing what the identity of our amine is. Even though this has alpha CH bonds, in this top example, doesn't matter. We're still going to go to an imine because a positively charged NH is easier to deprotonate than a CH bond. So even though it has alpha protons, they're not going to be touched if you have a primary amine. But if you have a secondary amine, then we're going to go ahead and form our imine. All right, that is all that I have for you today.